This lesson is on dot diagrams. Remember that dot diagrams come from valence electrons. Valence electrons are your outermost electrons. These come from the S and the P block. These are also what we call your bonding electrons. And so doing a dot diagram is going to be important to you because you're showing how many electrons are available for bonding. When you do a dot diagram, you have to remember to put the symbol of the element in the center and place the dots around the symbol to show all the valence electrons. Let's start with a simple one like hydrogen. Hydrogen has one valence electron. It's in group 1, and so everything in group 1 has one valence electron. Everything in group 2 has 2 valence electrons. Use the group numbers at the top of the table to help you. When you get over to something, say, like oxygen, oxygen is in group 16, so we take the 1 off or subtract 10, and it has 6 valence electrons. The maximum number of valence electrons that an element will have is 8. That meets the octet rule. So let's look at hydrogen. We would put hydrogen's symbol in the center, and in this case we would put 1 valence electron. Now it doesn't really matter if you put it on the right or on the left or on the top or on the bottom, as long as you show 1 dot or 1 valence electron. For oxygen, we would put O in the center, and now we need to fill 6 valence electrons. So we would put 1, 2, 3, 4, 5, and 6. Now, you could have had the 2 on the top, top and bottom. You could have had the 2 on the right and the left. As long as you have 2 electrons that are by themselves, that's fine. Generally, when we look at this, it generally makes kind of a box around the element, and so you'll see you'll have 2, 2, 2, and 2. So make sure that you have kind of a boxy look to it. Let's look at carbon. Carbon has 4 valence electrons. So we would put carbon in the center, and then we would add our 4 valence electrons. Normally, by itself, carbon would look like this. But because carbon is so good at bonding, carbon will take this electron from the top, and it will actually move it to the bottom. And so by doing this, it actually frees itself up to have 4 blank spots available. And so it could bond here, 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 and here. And so it's giving itself 4 available setups. Alright, if you have something that meets the criteria like Krypton, where it has 8 valence electrons, it's probably not going to do any bonding. There are a few that will actually go into what we call an expanded valence, and they will actually bond. But for the most part, when you get 8, they're not going to bond. This would be your noble gas family. Very easy. 1, 2, 3, 4, 5, 6, 7, and 8. And so they would go all the way around and make that nice little boxy shape we were talking about. Now, the joy of doing dot diagrams is so that you can see the bonding types that you're looking at. If you have something that is an ionic bond, remember in ionic bonds, you have one element that's giving away electrons, that's usually the metal, and one that's taking them, that's usually the non-metal. So let's look at NaCl. We would do the dot diagrams so that you could see how sodium has 1 valence electron, and how chlorine, who has 7 valence electrons, would work as far as dots are concerned. Sodium, being the metal, is going to give its electron away to that chlorine. So chlorine is going to have 8 valence electrons, and because it picked up that 1 electron, it gets a charge of -1. Sodium, because it gave away its electron, has nothing out here to show, and so it has a charge of +1. This is where your ionic comes from? Your two ions, positive and negative. And so that positive-negative attraction is what holds them together. If, let's say, that you have an ionic compound like BaF2, barium is going to have 2 valence electrons, and fluorine has 7. Fluorine and chlorine are in the same family, but you have 2 of these, so you have to draw both of them. What that means is that barium is going to give 1 electron here and 1 electron here. And so when it does, it becomes Ba plus 2, and each one of your fluorine becomes a -1. If you had a covalent bond, covalent bonds share, and so you would show the sharing of those valence electrons. Let's start with an easy one like CH4. This is methane. Remember that we said earlier that carbon has 4 valence electrons. So you would draw your C, 1, 2, 3, and 4. Each hydrogen is then going to bring its 1 valence electron and share. So this hydrogen is going to share with carbon. The second hydrogen is going to come in with its electron to share. The third hydrogen comes in with its electron to share, and the fourth one does the same. And so now each hydrogen has reached its max of 2 electrons because that's all they can get. And carbon now has 2, 4, 6, 8, and it's stable. Reaching the octet rule is very important for the elements. This allows them to have a stability. So let's look at one of the basic ones like water. Oxygen has 6 valence electrons. We just said hydrogen has 1, so 1 hydrogen comes in and bonds here, and 1 hydrogen comes in to bond here. Again, oxygen is going to have 2, 4, 6, 8, and be stable. This hydrogen gets to share 2, and this hydrogen gets to share 2, and everyone is happy. Sometimes, however, sharing means that you have to share more than 1 electron with someone, and so we can actually get into things that would bond doubly or triply. So let's look at oxygen, like the oxygen that you breathe. Remember that we said that oxygen has 6 valence electrons, so I'm going to draw this oxygen with 6. I'm going to draw another O over here for you, and we're going to give it 6. Now, obviously, these 2 O's in the middle here, they can share. You also have an extra O over here and an extra O over here. So what oxygen will do is it will shift this O over, this valence electron over, and it will shift this valence electron over, and it will put them in the center. And so by putting them in the center, you end up with 2 red O's over here and no red O over there, electron, and you will have another blue one here and nothing over here. And so to kind of clean this up, what will happen is you will end up taking away this, and you will end up moving them to the middle. And by moving them into the center, you will have 2 blue here, and you will get 2 red here. Keep in mind that oxygen did not change. Each individual still is contributing or has 6 valence electrons to work with. So you can see that this oxygen still has 2, 4, and 6, and this oxygen still has 2, 4, and 6, but by putting these in the center, they get to share all 4 of those. So that means that oxygen 1 here has 2, 4, 6, 8, And oxygen number 2 has 2, 4, 6, 8, and so they share all 4 of the ones in the middle. Both of them have 8, and they're stable. And this would work the same with triple bonds as well. I hope that this has been helpful for you, and thank you for watching.